Well, hello again, Science Warriors. Guys, today we're going to be going through our review for our Force and Motion exam. We're going to get down to the desk view and we're going to work through this whole thing so that you guys can make sure that you are thinking through and able to solve all of these types of problems and questions correctly. So let's go ahead and let's dive down into it. Here we go. Alright, you guys, so first thing we need to make sure that we do is that you got to write your name up here at the top. Okay, I got to know who you are if you're going to turn this in for your bonus 10 points on the test. Section 1 for potential and kinetic energy. These terms right here all can be found in your dictionary in the back of your journal. For instance, the first one, energy, we just turn. We find energy right here. We're going to copy down this definition. This is the ability of a system to do work. Energy is required for changes to happen within a system. We need to put that in, and we need to make sure that we know exactly what energy is. So use your dictionary in the back of your journal to help you with the first vocabulary section. Okay? We're going to go ahead and move down here to the second area. Okay, what are the two primary categories of energy? Well, they are potential and kinetic energy. Okay, these are categories that energy can fall into. To help us with 3 and 4, to provide a real-life example, okay, I want to remind everybody of Mrs. Scent. We have mechanical. We have radiant, which is light. We have sound energy. We have chemical energy. We have electrical energy. We have nuclear energy. And then we have thermal. Well, all of these can fall into one of the two categories of potential and kinetic over here. So this is a type of kinetic. This is a type of kinetic. Sound, travel, so it's also kinetic. Chemical is stored energy, so this is a type of potential. Electrical is an energy that moves, so that is a kinetic. Nuclear is actually the energy held within the bonds of atoms and molecules, so this is a type of potential. And then, of course, thermal, since thermal energy we learned can move, it is a kind of kinetic. So these are the categories, potential and kinetic, whereas these are specific examples. So, provide an everyday real-life example of potential energy. Well, you can do chemical or nuclear, or you could even say something like a roller coaster on top of the first hill, because that's where the whole ride gets all of its potential energy to turn into it rolling through. Okay? Provide an everyday real-life example of kinetic energy. Well, you could say something like riding a bike. Or you could make your list. We have mechanical. We have radiant energy. Will be a real-life example. Sound energy. We have electrical. And finally, in our list to Mrs. Scent, we have thermal energy. So all different kinds of things would work for answers here. This is just an overview of the whole concept relating it to Mrs. Scent. Okay? Alright, that should finish up the first page. Make sure that you have inputted all of the definitions from the dictionary here. Let's turn the page. Okay, question number 5 actually has 2 appropriate answers. And I'm going to circle one set in this color blue, and I'm going to circle the second set in red. Okay, so it says here, what is the relationship between potential and kinetic energy? Circle the correct choices. So, in italics, the relationship between potential and kinetic energy is that as potential energy increases or decreases, kinetic energy increases or decreases. Well, 2 ways that this can be correct. If your potential energy is increasing, and that means that your kinetic energy is decreasing. Okay, so as we go up a hill like this, we're building up potential energy, but we're losing some kinetic energy because we're going to kind of stop right here at the top. Okay, Now the opposite is true as well. Decreases, okay, if potential energy is decreasing, meaning we're going down the hill, that means that our kinetic energy increases. So either combination would actually work. All right. So as long as you have the correct pair, you have this question correct. Now question number 6, moving on, we are going to go kind of fast, everybody, so be sure to use the pause and rewind buttons as necessary. But it says here, in this diagram, which letter of the diagram represents the places where the cars on the roller coaster would have the most potential energy? Well, this is the highest point. This means this is where we'll have the most potential energy, so B. Which letter represents the place where the cars would have the most kinetic energy? Well, we need to find the lowest point. Well, out of all the ones that are labeled, D is the lowest point because that's where we're going to be going the fastest, okay, on the ride. Which letter represents a place where the cars would have the least kinetic energy? Okay, the least kinetic energy spot would be the same as where we have the most potential. So that would be at B. You could argue that F as well because it's the top of a hill, but it's not nearly as high as this one. So do keep in mind that our potential energy is higher here than our kinetic energy. All right, so F can technically be an answer, but our best answer is B because that's where the kinetic energy is the absolute least, because this is the highest point. Which letter represents the place where the energy could be changed from kinetic to potential? Okay, so that means we're going from speed and we're building it back up. Well, look, we are going up a hill, meaning kinetic is turning into potential at A, but it is also doing that at E. So in both places, we are seeing that happen. Which letter represents the place where the energy would be changing from potential to kinetic? So we're going to be going from a higher spot to a lower spot. Well, that would definitely be letter C. Okay, so going from potential to kinetic. Okay, do we have any others? No, we do not. Where in the diagram would the cars be moving with the greatest speed? So the fastest point. Well, that's going to be our lowest point where we have the most kinetic energy, and that will be D. Okay? So, very good. Hopefully you can deduce potential and kinetic energies through something like a roller coaster for your exam. Okay, for section 2, speed. You want to remember we round to 2 decimal places when necessary. So, remember, there are steps that you need to follow in order to work these problems properly, especially because not all of these are solving for speed like this one is. So, if speed throws a football 50 meters in 3 seconds, what is the average speed of the football? So we have to write down what we know. We know that we got a distance and a time. 50 meters went in 3 seconds. So then our second step is to set everything up. Okay, with our blank formula first. Then we fill it in. And then we have to do our math. So 50 divided by 3. We're going to get a 1. We're going to get a 6. And we should notice that we are going to get a repeat. Okay, but to do this properly, we have to keep it going. Okay, 18, we get 2, 0, bring that down. We know that our third spot is going to be 6. So if we want 2 decimal places, we have to take it out to 3 spots. Okay, so this number right here is going to tell us where our second decimal place, what it needs to do. So since this is 5 or higher, that's going to go up 1. So speed is going to be 16.67 meters per second. Meters per second. Okay, this is our final answer. Okay, here we go. Pretty easy. Got to keep it going. If it takes Ashley 3 seconds, so we know our time is 3 seconds, to run from the batter's box to first base at an average speed, so we're been given speed now at a 6.5 meters per second. What is the distance? So we're solving for distance. Well, we need to remember that we have the speed triangle there to help us. So if we're solving for distance, we're going to kind of block this out, and what's left is speed times time will give us our answer that we're looking for. So let's set up the formula. So if we're solving for distance, we know that it's going to be speed times time. Distance is going to be, our speed was 6.5 meters per second times 3 seconds. We do our math. Okay, so 6.5 times 3. Okay, and then we of course have one decimal, so we have to move it over. So 19.5 would be our number part. How do we know what measurement we're doing? What units? Well, we'll go back into our problem. We're working with meters, okay? Meters. So our final answer for distance has to be in meters. Okay? So we didn't have to round here because it came out nice and neat with less than 2 decimal points. Okay? So let's continue on to the next page, number 9. Alright, as we read, we're going to make our list. So Bart ran 5,000 meters. So that's a distance from the cops at an average speed, okay, so we got speed now, of 6 meters per second before he got caught. How long did he run? So we're looking for time. So again, we're going to use our triangle. We're solving for time. So we need to take distance and divide it by speed in order to get it. So T equals D over S. Time equals 5,000 meters over 6 meters per second. So then time, let's do our math. Divided by 6. Alright, and we are going to get 8 times 6, which is 48. 2, bring down the 0. We get 3, which is 18. Bring down this 0. 3, which is 18. Okay, we'll bring this up. And we can notice that every time we add a 0, we're going to have a 3. I have to add a 0 again, because that's going to be minus 18. Give us 2. I'm out of space, unfortunately. 3, and so we know it is going to go out and be 3 repeating. Okay, so we look here at the third spot to determine what happens to the second spot, and because this is 4 or less, the second decimal spot stays the same. So our time here is going to be 833.33. Now, what is our measurement of time in this problem? Seconds. We're going to put an S, and then we have our final answer rounded correctly. All right. Next, we have Justin races his Chevy S10 down Highway 37 for 2,560 meters. So our distance equals 2,560 meters. And our time was 60 seconds. What is his average speed? So we're solving for speed. Well, we know this formula. This is the basic speed formula. S equals D over T. Speed equals 2,560 meters divided by our 60 seconds. And now we've got to actually like do some serious math. This one's going to be interesting. Divided by 60. All right. So we're going to know that we can't go into 25, but 60 can go into this 4 times, so that's 0. Then 240, which gives us 16. Bring down our 0. 60 can go into that 2 times, giving us 120. We have a remainder of 40. So we add our decimal point, add our 0. 400. So 60 can go into 400 6 times. Okay, 6 times 0, 6 times 6 is 36, and we're going to get a repeating remainder. So I'm going to move this to over here so we can see 40. I'm going to add my 0, and we're going to have a 6, which is going to give us 360. Still have the remainder. We got to continue it out. Okay, going to give us here, and then our final one will be a 6, be 360, and we can stop. Okay, so we have 42 with 0.6666, all that repeating. If we look at our third spot, it is 5 or above. That means this 6 is going to become a 7. So our final answer is 42.67 meters per second. Again, double check, meters per second. That's our final answer. Okay, moving right along, here we go. Mike rides his motorcycle at an average speed of 20 meters per second. So we got speed is 20 meters per second. Okay, and it says for 500 seconds. How far did he ride? So distance is what we need. All right, speed triangle. We need distance. So it's going to be D equals speed times time. D equals 20 meters per second times 500 seconds. You need to make sure that you pay attention to your zeros on this problem because it is easy for you to make a mistake and not have enough zeros here. But we have 1, 2, 3, and of course we have 2 times 5, which is 10. So we're going to have 10 with 3 zeros behind it, giving us 10,000 watts. Well, we were in meters, so his distance was 10,000. All right. Cool. Working right along. Here we go, number 12. Sarah backstrokes, which is a swimming move, at average speed of 8 meters a second. How long did it take her to complete the race that it has a distance of 200 meters? So we need our time. We don't know what that is. So we gotta use our triangle. Okay, we want this. So it's gonna be time is distance over speed. Our distance was 200 meters divided by 8 meters per second. And let's do the math. 200 divided by 8. We get 2, which is 16. We get 4. We bring down the 0, and we get 5. And we get an exact, nice, neat answer. So here we go. Time is 25 what? We'll look in the problem. Speed was meters per second, so our time has to be in seconds. Final answer. Very good. Alrighty. Let's now go into number 13. Number 13 is a tough problem, okay, because it's not just asking us for the stuff we've been doing, it's asking us for a little bit more. Okay. Actually, I'm going to take a quick moment and clean the lens. There we go. That makes things a lot cleaner. Okay. So Lauren's SUV was detected exceeding the posted speed limit of 60 kilometers per hour. So we are going to need that information because that was the posted speed, but that's not what she was doing. So let's see what else they give us. How many kilometers per hour, okay, that's what they want us to work in, would she have been traveling over the limit if she had covered a distance of 10 kilometers in a time of 5 minutes? Okay, so our time given to us was in minutes. They want us to be in hours, so we're gonna have to do something here in a bit. But I think we can work this out the normal way and figure out an answer. And I'll show you the second way to get it as well. So we want to know speed, so distance over time. Speed is 10 kilometers in 5 minutes. So our speed is 2 kilometers per minute. So if you remember what this means, kilometers per minute, there's actually a 1 right here. So she's going 2 kilometers every 1 minute. Well, we want to know her kilometers per hour. So if we convert that, okay, we're going to multiply by there being 60 minutes in 1 hour. Okay, so this is called a conversion factor. When we do that, okay, 2 times 60 is 120, and it becomes kilometers per hour. What was her original speed? Or what was the speed of the area? Well, that was 60 kilometers per hour. She's going 120. The question asks, okay, in kilometers per hour, how much over the limit was she? So we have to take her speed she's going, subtract the speed that's posted legally, and we see that she is going 60 kilometers per hour faster than the posted speed limit. This would be a felony. She would go to jail and she would be charged with lots of bad things. This is going way too fast in that posted zone. That would be more than a ticket. Okay. The other thing you could do is you could use your conversion factor earlier to convert 5 minutes into a decimal for hours. This way seems more simple to me, but the other way does get you a more accurate answer. But this is how you can work a problem like that. Okay, especially if you're paying attention to what your units that everything's in. So speed is in kilometers per hour, posted on the sign. The question asks what is her miles per hour, but it gave you time measurements in minutes. You need to look out for when they switch things on you to make sure you're paying attention to your questions. Alright, so last one, number 14 on this page. Tina's calculations of the tarantula found that the spider was about to cover 20 centimeters, so that's a distance, in 5 seconds. What is the average speed? So now we're back to nice and easy speed. Speed is 20 centimeters over 5 seconds. So our speed comes out to be 4 centimeters per second. That's our final answer on that one. So ending up with this section with a nice and easy problem. All right. Hopefully if you have any questions that you go back and look at how we worked each of these. These do take a little bit of time, so you want to make sure that you are proficient with breaking down how to work each part. So we're going to turn the page now to the third section of the review, which is our distance time graph section. All right, this section, I had you guys write this down somewhere, hopefully in the beginning. Speed. Okay, if you have 2 points and you're trying to figure out, let's say, between point D, B, and D, to figure out speed of this section, we've got to mathematically take away this first part and the last part. So to do that, we're going to take the distance of the second point, which would be D in that case, and the minus, D1 over the time of the second spot minus the time of the first spot. So D minus B because D comes second. Okay, so that's our reminder for most of these. Alright, here we go. Number 15. Between which 2 letters is the rate of speed the fastest and why? Well, we can tell that just by looking at this, at the lines. Okay, we learned in class that the steeper the line, the faster the speed. So we have a straight line here, we have a horizontal line here, we have a curve, we have a straight line, and then we have another curve. Well, the steepest line is between B and C. So we're going to write down that between B and C, because this is the steepest part of the line. Meaning the speed is greatest here. Okay? So that's how we actually explain why. We have to pretend like you're not talking to the teacher. Okay? You gotta explain why as if you were talking to someone who doesn't know anything. Alright? So here we go. Number 16. The least amount of distance covered occurs between which two letters? So we're looking at, okay, how it's moving up the graph. So from A to B, it moves from here to here. B to C moves from here to here. C to D moves from here to here. D to E moves from here to here. And E to F goes from here to about here. So the place where we have the least distance covered is wherever we're going to have a horizontal line, or the smallest distance traveling in the upward direction on the graph. So for this one, it's D and E, okay, because no distance was covered, meaning they were standing still between these points. Okay, so we can just deduce that just by looking at the lines of the graph, okay, between D and E. Next, identify the type of motion occurring between letters C and D. Give evidence to support your reasoning. Okay, so C and D. C curves this way. Now, I showed you guys that if you take the center of your curve right about here and you draw an arrow coming from that, so notice how this arrow is going in the downward direction. This means we are decelerating. Okay, so we are decelerating. All right, and then we know this because the line curves towards becoming a horizontal line. Okay, so I showed you how you can just see it with the arrow, but our explanation of evidence is to, as you see, this, if I was to draw a line right here, this would be how steep it is. Right here, this would be how steep it is. Right here at point D, it's becoming a horizontal line, which means we have zero speed. Okay, so this is proving to us how we're going downward in our speed. All right, number 18. During the total journey, how many total seconds passed when the object was not in motion? So we got to go from here's D, follow the line. It's going to 14 seconds. E is 19. So this basically would be T2 minus T1, which would be 19 minus 14, which gives us 5 seconds. That's how long it was standing or sitting still. Number 19, calculate the average speed between B and C. So here we go. We need to use that helper. So speed is D2 minus D1. Keep writing I. I'm sorry, guys. T2 minus T1. All right, I'm going to work sideways because there's not as much room to go downward here. So let's fill it in. So the distance here at C, the second point, I'm going to estimate to be 42. Okay, if your estimate is a little bit different than mine, that is okay, as long as you work it the same way. All right, minus the distance at point B, which is about the same amount of distance up from this line, so I'm going to say that that's 12 over our time. So the time of our second point is 10 seconds, minus the time of our first point, which is 5 seconds. All right, and then we finally get, we simplify that to 30 over 5. And these were in meters and these were in seconds. So easy final answer is going to be 6 meters per second. That is how fast we're traveling between this point and this point, because when we subtracted these, we made this not apply, and we also made this not apply to what we wanted. All right, last question. How much distance did the object cover over the entire journey? Well, we just go up here. started at 0, and then we find our final point, which has gone the furthest, and we just take it back. And if we estimate, we can estimate that it's almost half, so we'll go ahead and just put 55 meters, because again, we're working in meters right here. Okay, and we're going to square it so we can see it clearly. The next two questions are on the back. It says to calculate the average speed for the entire journey from A to F. Okay, so this is pretty easy because all we have to do is take our total distance divided by the total time it took, and that's going to give us the speed we want. So our total distance, we just found that out to be 55 meters. Our total time to get here was 24 seconds. So speed equals 55 meters divided by 24 seconds. Well, let's do it. So 55 divided by 24, we get 2. We know we can go into that because that is 48. So we get 7 as a remainder. We bring our decimal up, add our 0. We know we can get it 2 more times. Okay, 48. So we take from there, we get 2, and then we get 2. So 22. We were close. And then finally we get, okay, when we add our 0, we can do 9 times. So 220. So 9 times 4 is 36. 9 times 2 is 18. 19, 20, 21. We get 4 as a remainder. Alright, we add our 0, we bring it down to here, and 24 can go into 41 time, so we get 24, so we have 16. Alright, but we have 3 decimal places, so we can stop. Alright, so speed is going to equal, well, that's 4 or less, so that 9 is going to stay the same, 2.29 meters per second. And that would be our final answer for the average speed of this entire trip. It did not go that speed very often, but because of it sitting still, decelerating, accelerating, all of these factors taken together, if we were to draw a straight line from here to here and calculate, that would be its speed. So that's very similar to what it's like in real life. Alright, so number 22, make a story. Here is my story that I have made up for this. You can make up whatever story as long as it makes sense. So here we go. Bobby, just picking a random person, started riding his bike. He sped up for 5 seconds. And then continued at a constant speed. Notice how I'm using the science words in my story, okay, describing scientifically what he's doing. Okay, for 5 more seconds. Now I got all that from the fact that we have acceleration. Okay, our arrow would go up. Okay, from 1 to 5, and then from 5 to 10, he went a constant speed. He came to a stop sign and slowed down before stopping for 5 seconds. Okay, let's double check. He did slow down and then he stopped for 5 seconds. Okay, so our story is matching. And then finally, we have to do that last part. Well, I just said that then he continued at a constant speed to his friend's house. Okay, because that would be a good place for Bobby to stop, was when he gets to his friend's house. Okay, so any story would be fine here as long as it includes that he accelerated first when at constant speed, decelerated and stopped, and then continued at a constant speed till the end of his trip. Okay, we needed to take each piece and make a piece of the story out of that. Alright, so we're going to skip over this, and we're going to move on to over here. Okay, to our final section, which is our inclined planes information. So, the illustration shows a wooden block being pulled up an inclined plane with a spring scale. What change in the experimental setup would require more force to pull the block up the inclined plane? So remember from your notes page that was handed out, the longer the ramp, the inclined plane, the less force it takes to move an object to a certain height. So if this is our height, and then this is our length, alright, we need to think about how can we make this where it's going to require more force to move the object from the ground to the top. Well, let's look. Okay, we want requiring more force. Okay, we can use a much longer inclined plane. Well, that can't be it because that would actually decrease the force. Force would decrease. Pulling the wooden block more quickly. Well, that's not right because it has no effect on force. Oops. Effect. Go. Alright. So, since that has no effect on the force, that can't be the answer. Reducing the mass of the wooden block. Well, if I reduce the mass, that would cause the amount of force to lift it, okay, go down. Because it would be easier to pick up. It doesn't weigh as much because it doesn't have as much matter in it. So that can't be it. Okay, and then increase the height of the inclined plane. So if I increase height to make it taller, let's say to go up to here, okay, and I don't change the length of my ramp, my ramp goes from being not steep to being pretty steep. Now, isn't that harder to pull up? Yes, it is. So this would cause force to go up. And so D is the correct answer. Okay, number 2. What is a disadvantage to using inclined planes to lift a heavy object? Well, remember, force decreases would be the advantage. Distance is going to increase when we use a ramp. That would be the disadvantage. So let's see what we got. The object must be moved a greater distance. Ooh, isn't that what we just said? So let's keep that one and check the others. Takes less effort to move an object. Well, that would be this. That would be a disadvantage. This is an advantage. Okay, to make less effort to move it, that would be an advantage. Many objects are difficult to lift straight up. That's true, but that would be a reason why to use a ramp is to make it less difficult. So that can't be right. Because that's just a random statement. It's true, but it doesn't have anything to do with this question. And then it says, heavy objects usually take up more space. Well, this problem isn't asking about it taking up space, so that can't be right either. So A is our answer there. Okay. Last 2. Which of the following decreases when an object is moving using an inclined plane? Okay, so we remember that force decreases while distance increases when we use these. Okay, so let's read it. The distance the object moves, that is not decreasing, that is increasing, so that cannot be correct. The pull of gravity on the object. Okay, so if that is increasing, this is staying the same, because gravity, does it change? Not really, not when you're on the surface of the planet. If we were a couple of miles up in the atmosphere, then we'd be talking some change. So this can't be it, because gravity is not going to change for only a few feet difference. Okay, C, the force needed to move the object. So the force needed to move the object would decrease if we use a plane. So that could be the answer. And then we have the amount of space the object occupies. Well, guess what? That stays the same. So D cannot be correct. C is the only final correct answer there. Alright, last one, everybody. When an object is lifted directly from the ground rather than moved with an inclined plane, which of the following would be increased? Okay, let's look. The mass of the object. That's going to stay the same because it's still the same object. We didn't change the object. The work done on the object. We haven't really talked about work specifically very much, but it's actually going to stay the same. Okay? The force needed to move the object. Okay, remember, we want to know if it has been increased. So force needed to move the object, that decreased. So can that be correct here? I don't think so. But let me double check. Let's see, y'all. The amount of friction acting on the object. We're going from lifting straight up to using an inclined plane. Friction would be what is formed when this box moves up. When we go from here up, there's not really a lot of friction, is there? So the force needed to move the object goes down. So C cannot be the correct answer. But the amount of friction, since this is touching the ramp and we're going up a certain height, okay, and this is just going from here to here, the same distance, but there's nothing touching it other than we're picking it up. That would definitely be a true statement, wouldn't it? So the amount of friction acting on the object would increase using a ramp. Okay? Alright, boys and girls. Hopefully, if you need to go back and relook at any of these sections, that you do so. But you should now have a completed test review. So now, all you need to do to earn your 10 points is to make sure that you have signed this line and that your parent or guardian who witnessed you studying for this test by using this video has signed right here. Bring this to me on Tuesday when you come to class, hand it in, and you will earn yourself 10 free test points to be used wherever you need them. Alright, everybody. Thank you so much, Science Warriors, for your time. I'll see you guys on Tuesday. Good luck. Make sure you study well, and I'll see you next time. Peace.